the cloud.
Okay,
Let's start.
Hello, everyone. My name is Anton Bozhedarov. I'm from Moscow Institute of Physics and Technology and Russian Quantum Center. I'm a PhD student and I'm working as analyst at quantum computing applications at industrial problems. And today I would like to talk with you about some useful tools such as quantum optimization tools that already works in practice and allow us to solve at least some small industrial problems. Of course, they not compete with classical application tools right now, but in future we expect that such quantum optimization tools will be very useful and could outperform existing classical solutions. And what's also very important that we could create some devices that are based on some ideas that looks and stands behind quantum computing, but we could solve and implement them on classical devices. And also will mention such devices too. So I will share my screen. Could you see the slides?
Yes, we see the Google slides, and if you
okay, so very cool. I will start with some like general intro to quantum devices. I will not explain in details like what the types of devices could be and why they different from each other. I will like mention some general ideas behind such devices, and then I will talk about like mathematical background when we're working with quantum computing, and then I will come to quantum optimization and will mention two very important quantum algorithms, how to implement them on different quantum and semi-classical devices. Okay, right now, and probably you have heard about universal quantum computers. They're very like hyper existing in social media and in some marketing companies like of Google, IBM, some of Chinese companies who are already working on quantum computers and etc. And such universal quantum devices will be able to solve any computational problem. So this is like of statement for the quantum computers. Should we use them for any problems? Of course not, but for some of them, for some of computational problems, universal quantum computers will provide computational advantage between in comparison with classical tools. And universal quantum computers could be based on different physical platforms like ion traps, ions, photons, superconductors, and etc. Some of them very good, some of them not very cool, but nobody understands how exactly to build quantum computer on which physical platform. Another type of quantum devices that are much simpler to build, but again, it's a really hard problem to build such quantum device, is quantum annealers. It's optimization special hardware that is built to solve only one particular problem, the problem of Eisenspin spin glasses, like spin optimization of spin configuration model. It is built like based on architecture of the device. It could solve only such kind of problem, but it could solve it really fast. And idea is once we build some device, at least one device that could solve such problems, we could build and solve any other like relevant problems. What's very useful right now, and like a lot of research here in these topics, is hybrid quantum optimization and quantum computing tools. Like when we use some part of quantum processor to solve only one part of computational problem, and we use classical hardware to solve another part of computational problem. And we combine these tools together to solve like very big problems faster than usual classical hardware, but of course, such hybrid scheme are not very competitive in comparison with the universal quantum computers. And very last like topic here is quantum inspired computing, when we use some techniques that was created first of all, for quantum computers, but somebody understands that we could use such techniques on classical devices. It's like for just usual CPU or for GPU cards, or even if we use special hardware like FPGA cards, like special purpose designed hardware chips that solve only particular problems, but solve them very efficient. So I will start like mathematical introduction from here, from kind of problems that are existing right now. And like, of course, it's not very precise description, but of course, in some sense, like general overview. We know some problems
Can we
dwell
on this slide just a little bit? Sorry, I kind of blinked. So are you claiming that quantum computers will solve NP-hard problems? And
no, of course not. So we don't know any device that or any techniques that could solve NP-hard problems, but we should understand that there are some NP-hard and P-hard problems that some devices could solve a bit faster than classical computers.
Okay, thank you.
Yeah, and so we what we can efficiently solve is P problems like multiplication of matrix inverse, sorting of arrays, solving some polynomial equations, and etc. So such kind of problems are belongs to P class of problems. If we extend some problems and some problems could be solved by non-deterministic Turing machine, such kind of problems we will like call as NP problems or NP algorithms. And if NP problems are equivalent to each other, then we call them NP complete. And there are some kind of problems like optimization, combinatorial optimization in particular, that are not NP problems, but NP hard. Yes, it's more hard problems that we know right now. And some kind of this NP hard problems is like traveling salesman problem, like we should optimize the road on the graph, like and visit every node of the graph and go over the graph with minimal cost of intersection between two nodes. And there is two problems that is known as Ising glass problem or Ising model, and equivalent of this problem is quadratic and constraint binary optimization. And there is some device that is the physical like meaning of the problem is equivalently to Ising problem. I will tell about this in more details. So, and right now, what we don't know, and everybody don't know, that P is not equal to NP complete, NP class of problems, whether they are equal or not. And if we could able to solve some of NP complete problems very efficient for polynomial time and for polynomial resources, it means that we could solve every of NP complete problems. So that is like very important part of trying to solve and find some algorithm to accelerate the solution of NP hard and NP complete problems. And here, like 5 minutes introduction to quantum mechanics and for quantum bits or qubits. So I will start with some like kind of introduction from here that quantum states could be represented as a vectors in Hilbert space, and they are normalized to one. And evolution of quantum state is described by unitary operator. And based on these facts, we could describe a lot of things like using just linear algebra. We could describe a lot of things that comes in terms of quantum computing and quantum optimization too. And we usually encode like classical bit, we encode them in quantum way. So when we represent any binary system, when we suppose that this system is quantum, it means that this quantum system could be in superposition because linear combination of quantum states like is also a quantum state. And from this fact, we get that qubit is not just binary system. It's like a sphere and could be described as a sphere of radius by 1. But what is very important is that we cannot like measure all information that is stored inside of the qubit, even if it stores like infinite number of bits or like based on precision of variables here, like we have alpha and beta. We should normalize this condition because every quantum state is normalized to 1, just because like from axioms of quantum mechanics. And we could like store in these numbers alpha and beta a lot of information, but we cannot measure or restore this information from from qubit by single measurement, because every measurement destroys the superposition of quantum states. And we, after we measure the qubit, we will get either 0 result of measurement or result that corresponds to 1. Because, for example, like a photon, it could be polarized as vertical polarization or horizontal polarization. We could have like any superposition of these two states, like vertical and horizontal polarization of photon. But when we measure it's in basis of vertical and horizontal polarization, we will get only 1 result of measurements. And in order to understand exactly what is exactly the numbers of alpha and beta, we need to have a lot of copies of the same quantum system with the same coefficients alpha and beta, and measure it a lot of time. And based on the statistics, we could restore these numbers of alpha and beta. But in single measurement, it's impossible to do. So we will get only 1 bit of information from 1 particular measurement. When we talk about like many qubits, very useful mathematical tool is Kronecker product or tensor product of vectors. So here you can see how it works with just a 2-qubit representation. For 3-qubit representation, it looks like we're the same. And when we describe qubit as a vector in quantum, as a vector in Hilbert space, it's very important to look that it's very similar to binary representation of integer numbers. So it's how to easily remember like representation or restore such kind of representation of qubits. When we talk about like operators that acts on qubits, it's also like unitary operators. When we will draw the diagram, how initial quantum state psi, when we act on this initial quantum state with some quantum gate or unitary operator, so it will be evolved, and we will get some new quantum state like u psi, and it's also quantum state, so it's normalized to 1, and this is how such kind of quantum evolution is described using the drawing and box notation. And when you have, if you have seen some of the quantum algorithms, like by picture, there are a lot of like boxes, wires, and etc., and they all represent unitary operators and vectors. So when we have like, how we could make several quantum, how we could make qubits in lab, there are different platforms like photons, superconductors, atoms, ions that builds and interrupt. We could use some structure of some crystallic materials and etc. So there are a lot of ways. Actually, none of them are very perfect. Like it's really hard to build a quantum computer. It's really hard computation engineering problems. Like for example, how to use a lot of qubits in single system and control and have precise control on every of them. So from here, if you have any question, like you could interrupt me at any time. I suppose that you know everything that I have talked about like previously in previous 10 minutes. So let's talk about like something more interesting in terms of optimization. So the basic idea behind adiabatic quantum computing is that we have some very trivial magnetic field, for example, or like in quantum computers and physics, we will call this as Hamiltonian, like operators that corresponds to energy of the system. When we have very trivial Hamiltonian or very trivial magnetic field, we will know precisely what is the optimal state of this trivial case. For example, when we have very strong magnetic field that lies along, for example, x-axis, and we have a lot of spins, like or magnets that is put in this strong magnetic field. All these magnets will be, or spins, they will be in correspondence with this strong magnetic field and lie on this axis, on x-axis. And this will be the optimal state of the quantum system. So it will be corresponding to minimum energy of the system in such potential energy field. But when we apply and add additional magnetic field, for example, on the axis of not x, but z axis, we will have additional energy levels that corresponds to the minimum of the energy of the system. And we will, for example, use a magnetic field along the x-axis. We will decrease this, this force to zero during the time of quantum system evolution, and we will be increasing the magnetic field along z-axis. And also we will add additional interaction between different spins, so that every spin could interact with its neighbors. And it means that the Landschaft or like the system will be in very complex magnetic field. And like just by looking at this complex magnetic field, we are not ready to understand, and it's really hard like to compute the optimal state of this very hard magnetic field, like in terms of the function. But from adiabatic quantum evolution, what we say that if we start with very, very trivial case, and we will add like a piece by piece some modification to this magnetic field or to this energy function, in the end, our system will be exactly in the ground state, like to the state that corresponds to the minimum energy level of this magnetic field. So this is based like on laws of quantum physics. It's proved and knows as it is known as a quantum adiabatic theory. And we could use such theory to compute optimization problems, to solve optimization problems. What's the general idea behind using such field? So when we have like magnetic field here, we could describe it as using some kind of optimization, using some energy function. And what we could do, we could encode any computationally hard or NP hard problems as a special kind of magnetic problems when we have to restore the position of or like direction of spins in the lattice. And when we solve these problems of energy of system configuration on energy landscape, then it means that we solved the problem of traveling salesman problem, for example, because we have correspondence between all of these problems. So the idea, like in that particular case, for example, so and we have device that very quickly could solve the Eisenspin problem, and when we could encode this problem as a traveling salesman problem or maximum cut problem or max sat problem, it means that we could solve such problem using Eisenspin model. When we describe this model in terms of mathematical tools, we could describe it in this way. So whereas S corresponds to position of the spin, either along magnetic field or in opposite direction, for example. So it could be like values of plus or minus 1. And the first part of equation here corresponds to interaction between spins. So we have a matrix J. The matrix here is symmetric. And the second part of the equation is like external magnetic field, when we have additional forces that acts on the system. So, and that corresponds to the Eisenspin model. And when we have square lattice or like planar lattice or chain, it is very like it's very easy problem to solve analytically. But when we have like 3D lattice, or like, for example, interaction different, not with neighbors, just interaction, but with high order of interaction, for example, between low right and up left spins, when we have such interaction, such problems quickly becomes computationally hard. And in general case, such model is NP-hard problem. So, and when we have device that exactly corresponds to solving this model, and when we like set up all the magnetic fields of this for this device particular, and we found energy configuration of the spins for this particular device, that we could solve computational NP-hard problem. Does it mean that we could solve NP-hard problem efficiently? Of course not, because there are a lot of like additional computational challenges.
Before you go to the next slide, Anton, can I ask a question?
From here?
How much time you spent on Eisen problem? But what if we relax Si to be continuous from -1 to 1? Does the problem still stay NP-hard? Well, right now it's just a counting problem, and that's the problem. We have to like consider all of the permutations. But if we make it continuous, with I don't know if you know the answer, but like, have you looked into that? Did people consider that?
Yeah, I'm not sure this problem will remain NP-hard. Probably not. Like, I don't have exact answer, but
okay, never mind. Just, I was just curious.
Yeah, it seems that the problem will not be NP-hard problem when we have relaxing, but solving this relaxed problem, it does not guarantee that we have solved NP-hard problems in initial way. And such like relaxation is one of possible application how to solve them in real on classical devices. And such tools are like very useful in practice, really. What are problems like for implementation of this device, like for solving quantum problems? Yeah, it's like we could draw, for example, the energy landscape of the ground states. And from 0 time, we have very trivial case for the magnetic fields, like it's very strong and acts, there are no interaction between spins, and only strong magnetic field. So like energy very precisely and very known, like ground state or state that corresponds to the optimal or minimum energy of the system. But when we apply additional magnetic fields, like when we increase the action of interaction between spins, when we add additional magnetic fields, the problem becomes more complex and NP-hard actually. And when we haven't achieved like, do we have some equation here? I'm afraid that not. But in general case, we start with some trivial example and goes to exactly the problems that we would like to solve, like the target Hamiltonian. And in intermediate states, there is a gap between the ground state of the energy, like the minimum ground state, and the first excited state of the system. And at some point of time, like sometimes of this evolution process, the system could jump from ground state to the first excited state, or if we have a lot of noise in the quantum device, or like some temporal fluctuations and etc. Sometimes it happens just without no reason. And the less the gap between ground state and the first excited state, it means that the higher probability that our system will jump to the first excited state, or even like for second or third excited state. And when we continue to like add additional forces and additional magnetic fields, the system will not be in the ground state of the target Hamiltonian, but at some like higher energy levels. And this is like real problem for nowadays device, because nobody able to cut off every interaction between quantum device and its environment, or any temporal fluctuation. That is why we need to build, for example, if we use superconducting qubits or qubits based on atoms, we need to store them in very cold places, like for cryostats that are like almost zero temperature, in order to provide such a safe place where there is no temperature fluctuation here in the system. And what like corresponds to adiabatic evolution, it means that we will not like jump from ground state to the first excited state. Of course, it's very long process. It should be a long process, but we are not able to solve such problem in terms of engineering, and we need to have trade-off between systems that are not completely adiabatic because it's too quick for adiabatic evolution, and from the other side of the engineering problems, that we preserve the coherence of the qubits between each other. So they will not destroy the system by itself.
So can I have a question?
Yeah.
So this adiabatic problem can be related to the problem of salesman, right?
Yeah, like we could encode traveling salesman problem as an Ising problem. And
so in this case, what does the ground states, different ground states, excited states have to do with it?
When we have, like, for example, when we have first, like the ground state of the problem corresponds to the optimal path between all nodes on the graph. And the first excited state may correspond either to infeasible path. For example, when we have violated the rules that we should walk only by edges between graphs, between nodes. So for example, we could jump between nodes that don't have edge between them. Or we could, for example, choose another path that is not optimal. So this is like the first excited state, could be. In most cases, we create system in such way, like we encode system in such way that infeasible paths and infeasible solution have a very high energy, but solution with like very low energy corresponds to the optimal path between nodes on the graphs. And when we violate and jump to the first excited state, it means that we have jumped to the not optimal solution, but it will be close to the optimal. And currently, in terms of like using such devices for solving the Eisenspin model, there is a device that is called D-Wave quantum computers. It is based on superconducting spins, or superconducting qubits. It's not on the slide, unfortunately. Here, there are some devices that mostly classical than quantum, and such devices is built exactly to solve Ising problem. The scheme on the left corresponds to the coherent Eisen machine. It's an optical and electronic optical device that have a lot of fiber optics, and like we have pumps this optics with single photons, like there are electromagnetic fields that corresponds to singular photons, and every loop we read this the state of the photon, and based on the reads that we have measured, we apply some additional phase modification. For example, add additional phase for polarization of the photon. And such optical device could solve Eisenspin model approximately about 100,000 of spins. And it solves such problem. It finds optimal solution about almost for 5 or 10 minutes. So it's a really cool device But what is really important to know about this device, it's not purely quantum device. It's mostly like classical device because all computation happens not at the fiber optics, but it happens in the electronic devices. So there are a lot of FPGA devices, like special hardware designed to solve exactly one kind of matrix vector multiplication that is corresponds to the Eisenspin model. And such devices able to solve like hard problems. Of course, they're not like very precise. Sometimes they solve problem not very efficient and found not ground state, but like near the global optimum. But again, they work and solve some problems very good. Such kind of devices, some of them works even without the electronic components, without FPGA. So they works only on integrated photonics, but these devices are not very big in nowadays. So they could solve like about 10 or 100 of binary bit strings. So it's not very important right now, but they will be very fast in the future. Another type of devices that are completely classical and don't use any of the optics or any unknown physics to store and proceed with information is FPGA-based chips. So they produced by Fujitsu, for example, and they have built such device to solve Eisenspin model for 10,000 of digital spins. So, and they used like specific architecture of this device to solve this problem more efficient than classical CPU or classical GPU. I would like here to say some cases about how to use Eisenspin model in order to solve, for example, bin packing problem. Bin packing problem, what does it mean? That we have some assets or stocks, for example, or some useful elements that we would like to place in our pack. And for every element corresponds to types of numbers. First number is the cost of the asset. It is encoded as W. And another type of variables that corresponds to the assets or stock is future income. And your problem is like you would like to create assets or combination of assets that will guarantee you the most, will maximize your income in the future, but you have very limited budget right now. So you could not buy every of them, and of course you limited by budget. So, and your problem is to maximize your future income, but stay in constraints that your current budget or your current amount of money are very limited right now, and very limited by some parameter here. And for using such or solving the way of solving such problems with Eisenspin model or with for adiabatic quantum computers is when we build Hamiltonian or energy function, special function that is built with two separate terms. One term corresponds to the problem that we're trying to solve, to the cost function. It corresponds to the h with index p. And another term is h with index c that corresponds to the constraint of the problem. Probably Lagrangian optimization tool technique very similar to this kind of problem that we used not constraint optimization, it was constraint optimization, but right now we have unconstrained optimization model, but our constraint is added to the cost function here. Of course, we could have some additional weights before HP and HC terms that corresponds to the, for example, should we violate the constraint or not? So we have hard constraint, we have soft constraint, if you have hard constraints, it means that the weight of this constraint in the final function, energy function, should be much more than the weights of the target cost function. And when we encode such problem using Eisenspin model or Kubo model, I will describe Kubo model in next slides. What is the difference between Kubo model and Eisenspin model is Eisenspin model corresponds to 2 bits of like coding of information, 1 or -1, and Kubo model is the same, but we use 0 or 1s encoding. And here I will show like Kubo encoding of this bin packing problem. The first target cost function corresponds to the binary variable here, and you could see the binary variable here on the left side with classical problem. The variable x corresponds to the decision variable, like should we add or should we buy the stock right now, or we should leave it untouched. So, and when x is equal to 1, we add this stock to our assets. So here you can see that target function didn't change so much, but when we encode the inequality as a constraint and add this constraint to the Kubo model, like to the cost function, we use 2 terms here. The first term corresponds that we solve difference between like the weight of the problem, like the limiting factor of our budget. Yes, like the limited amount of time that we amount of money that we have right now, and like the cost, the current cost of the assets right now. And in terms to constraints to be satisfied, this function should be equal to 0. You could see here d times y with index d. It corresponds to binary representation of the variable w, the big W. So it's attempt to add additional binary variables and encode the real number w as a representation of the bit strings, like with additional weights here, like as an integers. And we have the last term in the constraints that exactly one operation of or exactly one solution should be found. So there is additional constraints here that we apply. And when we found such optimism, like when we will found the minimum energy of this function, we will find the solution to the problem that corresponds to the bin packing problem.
Are the YD and the DYD, are those binary variables or?
Why we use DYD?
No, are they binary variables or? No.
It's additional binary variables, yes. Like it's probably better to draw. So when we work with classical, with quantum here, or in code, we could forget, for example, about that we work with quantum. Let's work with classical, but with binary problems. In order to add these constraints as a like to add this to target or to final Hamiltonian, to final function, we turn this into equation. And in order to turn this into equation, we should add additional unknown variable, like to some y, big Y. And we represent this big Y as a bit strings here, and the maximum that we have as a bit strings is such representation. So it's like order of how we represent binary here. Or for example, I think that it may be confusing, right, from my description, because on practice we use binary representation in this way, like 2 to the power of d yd. But it was like what we use in practice. But here you can see like one hot encoding. It guarantees like we have a bit strings. For example, here we have like it's better to draw here. Like we have several bit strings here. It could be 0. For example, if we have a spin that corresponds to the 1 on the place here, it corresponds to the number 1. If we have integer 1 here, it will correspond to the number 2. If we have one integer here, it will correspond to the number 3. When we have number 1 here, it will correspond to the number 1, and so on. And that means that we have only one bit that is equal to 1 on the bit strings here. So exactly one bit that equal to 1. So this is the constraint here. And we encode this W as a bit string in such one hot parameterization.
Basically trying to encode NP hard problems, right? This is just a way to encode NP hard problems, is that right?
Yeah.
Okay.
It's a way to encode for the hard NP hard problems. It's bin packing problem is NP hard.
Right.
And this is just a way, one of possible solutions, how to encode this as a Ising or Kubo model. So Kubo model is also an NP hard problem in such way, and Ising problem is also NP hard. And this is when we add constraints to the Hamiltonian, to the final Hamiltonian as a additional term to the function, not as a constraint. So, and we will look to the minimum of the final Hamiltonian to the H, and when constraints of the problem, like for the bin packing problem, are satisfied, it means that here we have exactly only one bit. Yes, it means that all strings will be filled with zeros except only 1 point, except only 1 bit. So it will be 0 here, 0 term. And when the constraints that this equal, wx equal to w plus some bit string y, this also will be 0. And what is left that we should minimize exactly this this term, that corresponds to the HP.
I have a question.
Yeah,
So,
yeah.
Is it true that when we find the optimal state of the spin of these particles, isn't it true that the energy field will collapse because we're observing them? Am I
It
thinking
will
about it wrong?
no. It will not collapse. It will mean that we have found the minimum energy of the system. So again, we have some quantum system. We act on this quantum system with some magnetic field, so with some energy, potential energy field, and the state that corresponds to the minimum energy, that's known as a ground state, corresponds to the minimum energy of the system. So, and the idea is to encode the the problem of interest, or the problem that we would like to solve, encode this problem as an energy function, and then apply adiabatic transformation. So we start with some H0, that is a very trivial case of the energy function, and we, during the time, goes here, to the problem of interest. And once here, we was at initial state, and we have found ground state of the system by the construction, because it's very trivial, and we have set up the system to be in the ground state of this 0 Hamiltonian. At the end, we also will be in the ground state that corresponds to the solution of the problem. That is the idea behind adiabatic evolution and encoding of the problem of interest or some NP hard problems into Ising model or Kubo model.
So,
but there is no guarantee that we will actually stay in this ground state, because there are lots of fluctuations in the system. So it's a way how to build such system.
But to collect the ground state, you still need to do multiple measurements because of the destructive nature of measurements, right?
Oh, no. Oh, I got the question. No, we have like what we use here is that we construct the Hamiltonian in such way that once we measure the system, we will be obtain the optimal solution. So it's okay to measure it only once. In perfect situation, when we don't have noise, when we don't have fluctuation and jumping between different states, measure the system just once and you will find optimal solution. But there are like cases when we have not applied or found like optimal energy in the system here, and we have jumped like on the higher energy levels, and you need to do this computational procedure several times, at least like 1,000 times, it will be good enough. Once you repeat this procedure at least 1,000 times, you will get like a distribution between several solution obtains, and you choose the solution that is most that has the lowest energy.
So can you comment on what is the computational theoretical difference between that Fujitsu chip, and which I understand is like an analog computer, right? And quantum algorithms, are they asymptotically equivalent, or there is like asymptotical difference in terms of which class of problems, or like say Fujitsu chip can solve it in 2 power 2 or like 2 power n, and like this is 2 power n squared, or like what's the difference? Computational, not physical implementation. Are they the same power or not?
Yeah, in terms of computational, there is no difference between classical processor, like that is based on classical transistor on silicon. There is no difference between Fujitsu and just like GPU card or special ASIC card, like for.
Oh, so it's not an analog computer. They're not.
It's not analog. It's digital computer.
It's still digital. Okay,
it's
just
still digital.
specialized.
Yes. Yeah, it's like the connectivity between transistors are different in order to easily implement such system and to accelerate the computation of such function. That's the difference. For example, you have ASIC cards that is a special hardware devices that is built specially to compute hash function to Bitcoin mining, and they're not they're able to solve another problems, but they're not like very fast as a CPU or GPU card in terms of like matrix multiplication, for example. And you will not use GPU card for other problems that are relevant to matrix multiplication or matrix vector multiplication.
Yeah, I get it. But my question comes from the fact that quantum computers look like just a special kind of analog computers.
Yeah. So in such model, when we have adiabatic evolution, the quantum computer is analog computer. And that's the difference between like digital computer or digital model of quantum computer and adiabatic computer. In ideal case, adiabatic and universal quantum computers are equivalent, but in order to use them as an equivalent of each other, we have to like implement any type of Hamiltonian here in the end. And this is not possible on current devices of adiabatic evolution or quantum annealers. And universal quantum computers are not so powerful because there are a lot of noise in the system, and qubits are not stable like during the time.
We have 5 minutes. Do you have more slides? It's unclear if.
Yeah, I have several more slides, like with explanation of QUBE model, like in general term. And I would like to show you some. I will share the presentation with you. It's okay to use, and I will try to briefly general overview of the discretization of this quantum adiabatic evolution process on universal quantum computer. We will need two or at least one formula that is used to implement adiabatic quantum style on universal quantum computers that is based on discrete gates. And this formula is known as Trotter-Suzuki decomposition. Like when we have matrix multiplication or exponential form of matrix, when A and B are matrices, not just numbers. So we could describe them as a multiplication of matrix exponent for each of them, but we need to take like limit for the infinity here. And you can see that this multiplication here are repetitive, like infinite number of times, and we would like to cut off at some point, for example, like fix not n to infinity, but some number like, for example, r. And it means that we will have error in representation of such function here. And the question is like how big the error is. And also what is useful or what is used in universal quantum computers, that like representation of these individual terms, like the term 1 and term here. And these terms that corresponds to the like H0, this is initial Hamiltonian. It used as a like several gate with index B, and this is known as gate with index C. And they are based on some parameters, and such parameters, for example, like the general form of the algorithm that is used to discretize adiabatic quantum evolution. Like this is the general scheme here. We have first term that corresponds to the UC, like the adiabatic Z target Hamiltonian here. It's many qubits gates. We apply this many qubits gates to the initial state of the qubits. Then we apply rotation along x-axis here that corresponds to the initial Hamiltonian here. We apply this procedure several times, like finite number of application. In the end of the process, we measure a lot of times. We measure this procedure. We obtain some function.
Anton, apologies for interruption. Let's leave details out. We have like 3 minutes. Why don't we stop here, and we have time about one question before the next meeting and the talk that everyone is invited to, the DIMA.
Yeah, sure. Yeah, sure.
So thank you for the talk. But anyone has any questions about? Maybe you want to order the adiabatic quantum computer device and solve you the hard problem. Can we order the device? Is the device available? Or
yeah, you can. Yeah, you could buy it.
I have one question.
Yeah, go ahead.
Is there a way to encrypt backpropagation for the quantum computers yet? Or is that something that's going to happen in the future?
Gradient descent.
Gradient descent, yeah.
You can get the optimal solution.
Yeah, that would be nice. Once
Just one.
constant time.
For that problem.
Yeah. So you know?
Yeah, the question is, can you perform gradient descent on quantum computers?
Yes, you can. Sometimes it's much like easier in asymptotic way to solve the problem as gradient descent, but usually like it's better to solve like NP hard problems, not gradient descent. Like the advantage of using quantum computer to solve gradient descent is not as much big as for solving another kind of problems. For example, number factorization, multiplication or finding inverse of the matrix, and for example, unstructured search in the elements.
Okay, sounds good. Thank you so much for the talk, and please share slides. We'll put them online together with the recording. And thanks everyone for coming. DIMA talk is just starting, so you're all welcome to join the DIMA talk.
Okay, thank you very much for your attention. It was a pleasure to talk with you.
Likewise, thank you.